Hi, this is a quick run through of AQA Physics A-Level 3B, Paper 3B, Option A, Astrophysics for 2023, just with some model answers and some discussion. So, let me see if I can get the screen off so I can go to the actual answers. Here we go. So question 1 is to draw a labelled diagram to define the parsec. Now remember, the parsec is defined as the distance to a star that has a parallax angle, that's this angle here, of 1 arc second, which is 1/3600th of a degree, because there are 60 arc seconds in an arc minute and 60 arc minutes in a degree. That is how far away that star will be. We have to make sure we label on this diagram the fact that there is 1 AU, 1 astronomical unit, between the Sun and the Earth, and then we have our parallax angle labelled. You don't have to draw the bottom version of this here, I just like to draw them both. This is how the Earth will go around the Sun in a year, because this is why we get the parallax shift, because you'll see the star at a different perspective when you're here compared to background stars. And you can label either of these lines 1 parsec, because in the grand scheme of things this distance is so big compared to this distance, because this angle is so small that they're essentially small angles apply, therefore we can say that. So yeah, you had to do quite a lot there for 1 mark. You needed to write 1 PC, 1 AU and 1 arc second, or 1/3600th. You did not have to label the Earth and Sun, although you could get away with not labelling 1 AU if you wrote Earth and Sun, because then it becomes clear. So then we go on to 1B. So we've got here the data for 2 stars, Regal and the Sun, and we have to know the spectral class of Regal. Now this is where knowing this table off by heart is really important, which is not the easiest set of numbers and things to remember, but it's something that is worth doing, because we can see there that Regal must therefore be in the spectral class B, because it has a temperature of between 11 and 25,000. So we're going to jot that down. Here we go. 12,000 is between those two. You need to learn that table. And then we're told that the apparent magnitude of Regal is 0.11, and we can see here that the absolute magnitude is -7.84, and we need to calculate in parsecs the distance from Regal to Earth. Now remember, weirdly, the more negative, apologies, that was my emails, the more negative the absolute magnitude or the apparent magnitude, the brighter the star, and the less negative. So for example, if we had a star that had a brightness 10 compared to 5, 10 would be dimmer, which feels very weird, but there we are. We're going to use this equation to compare absolute and apparent magnitude. So apparent magnitude minus absolute magnitude is 5 log d over 10, and this distance will be in parsecs. This is how the equation works. It works with parsecs. So you can see I made some silly mistakes with my minusing, because I didn't have a calculator when I first started doing this, and then I realised to just use my head a bit better. So we've got our apparent magnitude 0.11 minus our absolute magnitude, which comes out as a plus, so 7.95, and we're going to divide that by 5 to get log d over 10. Then to get rid of the log, we're going to do 10 to 7.95 over 5, which is 1.59, and we multiply that number by 10 to get 389, or we can round that to 390 parsecs. So make sure you're okay with how to use that equation. The log stuff can be quite tricky, especially if you're not an A-level physicist. And then we get on to part D, which has this Hertzsprung-Russell diagram, and it asks to draw a line on the figure above to show the evolution of the Sun from formation to white dwarf. And this is something that when I teach it, I don't really think about the protostar stage, I just think about the main sequence and so on the HR diagram, so there's some learning to be done here. So remember, the HR diagram has some funny scales. Once again, they are logarithmic, and the y-axis is essentially brightness or luminosity, or here absolute magnitude. The higher up the axis, the brighter the star, the lower down the axis, the dimmer the star. The x-axis is essentially temperature, and what is a little bit weird here is it goes from hot to cold, so it's like a negative axis. It's once again logarithmic if you were to do it in degrees Kelvin, not degrees Kelvin, just Kelvin, but here they've done it in spectral class. So the first starting point for me here is to know that the Sun has an absolute magnitude of 5 and has a temperature of about 6,000 Kelvin, which means it's in class G. So I'm going to find where that sun's going to be when it's on the main sequence. This is kind of the middle point, and I know that it's going to do, because it's a medium mass star, main sequence to normal giant to white dwarf. So that's a bit easy. So you get a mark for the line from main sequence to giant and a mark from the line giant to white dwarf. It's not that you get a mark for here, here and here. It's for the lines in between. You don't have to have arrows. If we're thinking about a protostar is very cold and very dim. So it's going to be over here in the cold side and the dim bottom area. So as long as your line starts somewhere here and then goes to the main sequence section, you're going to get the mark there. So your 3 marks of the, well, it isn't 3 marks, it's 1 mark, is for those 3 different lines. So I've done 3 ticks. So ignore that mark for each line is wrong. You have to have each line to get that one. Okay, then this is a mean question. One stage in the evolution of Regal includes the emission of a gamma ray burst. Outline the circumstances during which a gamma ray burst will be emitted by Regal. Well, if we go to the table again, Regal is 12,000 temperature, and we know that's spectral class B, and a magnitude of -8 almost. So it's going to be here and here, so it means Regal is a supergiant. That means that it's going to turn into either a black hole or a neutron star via a supernova. And the gamma burst event, I would argue, happens during the supernova, which is the collapse of the supergiant into a neutron star or black hole, with then kind of like bouncing layers essentially. The mark scheme, you got the marks for the word collapse, and I think a lot of people have fallen down on that. And then also to say that it's as it's forming a neutron star or a black hole. You can get the word supernova in there and still get the mark, but you wouldn't get a mark for the word supernova, which, like I say, is mean, because if you look on Wikipedia, it says a gamma ray burst happens during a supernova. I think the exam board wanted to distinguish that it was during not like a type 1a supernova, so it was during a supergiant becoming a neutron star and during that process. But we're going to learn from that. So gamma ray bursts happen during the collapse of a supergiant into a neutron star, which is a supernova. Okay, moving on to question 2, our telescope question. So state what is meant by the normal adjustment when applied to an astronomical refracting telescope. That is a telescope with 2 glass lenses, as beautifully drawn as a diagram here. The main answer actually on the mark scheme is this one here. This causes the image to be at infinity, or the arrangement that causes the image to be at infinity, the final image. The way I think about it, I think the easier definition, is it's when you have these 2 lenses so that their 2 focal lengths line up to give a focus here. So the distance between the 2 lenses has to equal the focal length of the objective lens plus the focal length of the eyepiece lens. And in the mark scheme, it says if you say equals f0 plus fe, you have to say where f0 is the focal length of the objective and fe is the focal length of the eyepiece. So just be specific there. And then a multiple choice almost. Which combination of lenses gives the largest angular magnification when used as an astronomical telescope in normal adjustment? Well, all astronomical telescopes are going to be using 2 converging lenses. They won't use a diverging and a converging. So that's going to get rid of 2 of our options. It has to be either 2 or 4. And then we're going to use m equals f0 over fe, which is in your formula sheet. I've just done it for both of them. So 5 over 100 is this one here, which gives me a magnification of 0.05, which is smaller, so not going to be that one. The other one is 100 over 5 here, and that gives me 20, so it's going to be the best one. Then we've got 2 stars in the constellation Orion. V1031 appears 40 times brighter than WASP 82 when viewed from Earth and has an apparent magnitude of 6. So what would the apparent magnitude of WASP 82 be? Well, if V1031 is 40 times brighter, we can work out how much more magnitude it must have, because remember, in that weird scale, every step of magnitude, so every time you go up a number, you go 2.51 times brighter, although it's actually down a number. So if you're going from 2 to 1, that then becomes 2.51 times brighter. So that means that 2.51 to the x must equal the 40 times brighter. Now to work out x, we have to do log 2.51 40, and some calculators will do that. I'm still on a natural log calculator, as I call it, a natural display calculator, which doesn't have that function. But what you can do instead is use this rule, that is log to the a b equals, I always use ln for this, ln b divided by ln a. So here 2.51 is my a and 40 is my b. So this is going to equal ln 40 divided by ln 2.51, which comes out as 4. So if you want to, you can also do this by trial and error. You could say 2.51 to the 1 equals what? 2.51 to the 2 equals what? And find the one that is closest to 40. That was also allowed. So if V1031 is 40 times brighter than WASP and has a magnitude of 6, that means it's just about visible with the naked eye. Remember, the higher the magnitude, the dimmer the star. WASP is dimmer, and V1031 is 40 times brighter, so WASP is 40 times dimmer, which means it has 4 more magnitudes. So we're going to do 6 plus 4 to equal 10, because it's going to be not visible with the naked eye, which is part of the next question. You will notice on the mark scheme that you get 1 mark for essentially getting the answer, and then the other mark is for like any of these 3 things. So if you didn't get the right answer, you're not going to get 2 marks, but if you either did this, or you added whatever you found to 6, then you can get a mark there, because it is quite a tricky question, I think. So then, as we've said, V1031 is only just visible to the naked eye because it's got a magnitude of 6, and if it's visible to the naked eye, you're using your eye essentially as a telescope. You've got a diameter of 7 millimeters. So can she observe the dimmer star WASP using a telescope with a diameter of 60 millimeters? And it says support with a calculation, so do a calculation. So here we need to know that the collecting power of a telescope is what tells us how bright or dim an object we can see, and it's proportional to d squared. So for this telescope, which is 60 millimeters compared to our 7 millimeters for our eye, the telescope's going to have a 60 divided by 7 squared times greater collecting power than the naked eye, and that number comes out of 7374. So the telescope can see something that is 73 times dimmer than our eye. If WASP is 40 times dimmer, then yes, they should absolutely be able to see that with the telescope. And then this is a bit of a gift of a question here. So CCDs are often connected to telescopes. Explain 2 reasons why this improves the ability to observe dim stars. Explain means what and why. You get 2 marks for 2 whats, and you get 1 mark for one of the whys. That doesn't mean you shouldn't write 2 whys. I've got 4 whats and whys here, so plenty of things we can say. So firstly, they have a better quantum efficiency, which means that more of the photons that reach the I have no idea what I wrote there. It should say lens, are detected. Oh, sorry, it says device. There we go. The device are detected. So your eye only has an efficiency of about 4%, I think. So only 4% of photons actually register, whereas it's much higher in a CCD, like up to the 80%. So you can see much more dim things because fewer photons reaching it can still actually give a reasonable image. We can have long exposures. You can't keep your eye open for a very long time, whereas you can keep the CCD on for a very long time. Also, you can build up pictures over time. So you could take an image of the same star every night for a year and combine all those images together. And that means we can collect more light, because the longer that it's on for, the more light can basically get into the light bucket. That's what I often call a telescope. They can be operated remotely, whereas your eyes can't. So you can put them in places where light pollution and atmospheric distortion is lower, so up mountains, in deserts, in space is the best one to get rid of atmospheric distortion. It will also get rid of light pollution, but we can get rid of light pollution by going to the desert. And that's much cheaper and much easier and much safer. And they can detect more wavelengths that go into infrared than the eye can, so it means we can collect more energy from the star. So loads of easy ways to get the marks there. That's a nice question. Okay, question 3, state the defining property of a black hole. Another kind of exam thing to learn. So they don't want you to say that gravity is so great that not even light can escape. They want you to say that the gravitational field strength is so great that not even light can escape. Or we can define it in terms of escape velocity, i.e. the escape velocity is faster than the speed of light. Either of those is fine. We then have a question about radio telescopes and normal telescopes, so the EHT and the Hubble telescope. and we've been given their aperture and their wavelength, their operating wavelength. As soon as I see a diameter and an operating wavelength, I'm thinking, this is about resolving power. This is about working out the Rayleigh criterion, which is, remember, the smallest angular separation between two objects that telescope can resolve, can see as two things. So galaxy M87 is 5.3 times 10 to the 7 light years from Earth. The supermassive black hole at the centre has a mass of 6.5 times 10 to the 9 the mass of the Sun. The radius of the event horizon is r. The astronomers propose to use either the EHT or the Hubble to observe stars whose distance from the centre is less than 1000 r, so they're less than 1000 r away from the middle of the galaxy. Discuss with calculations which telescope is more suitable for this observation. Well, as soon as I see the word event horizon, I think, I need to work out the Schwarzschild's radius, which is the event horizon, and this formula, remember, is given to you in the formula sheet. So 2gm over c squared, so 2 times g times mass, which is going to be 6.5 times 10 to the 9 times the mass of the Sun. That is on your formula sheet on the front page, not on the astronomical section. And we're going to divide that by 3 times 10 to the 8 squared. And that gives us a Schwarzschild radius of 1.9 times 10 to the 13 metres. So then, if I think about what am I trying to look at, well, if this is the black hole, it's trying to look at a galaxy that, and we're looking at stars that are within 1000 times the Schwarzschild radius. So this kind of diameter, that's the radius, that's the diameter. So this distance here, the opposite distance here, is 2 times 1000 r, because this is small angle, so we can say that tan theta is approximately theta, which equals opposite over adjacent, and once again, the fact that it's not technically a right angle triangle doesn't really matter. So that's our opposite, and then our adjacent is basically any of these, because they're all going to be basically the same, and the adjacent is our distance, we're looking at it here from Earth. So the distance from Earth, which is, we're told, 5.3 times 10 to the 7 light years, and I've done here 5.3 times 10 to the 7 times, this is 1 light year in metres, and it's 5 times 10 to the 23 metres. So I'm going to divide that, and I get that the angle that I need to be able to resolve, the angle between a star here and a star here, is 76.5 times 10 to the minus 9 radians. It's tiny. So now I'm going to go back up here and work out what is the Rayleigh criterion for each of these telescopes. It's the wavelength divided by the aperture. And I find, don't forget nanometers or millimeters, but I find that the EHT has a Rayleigh criterion of 1.0 times 10 to the minus 10, that's what that says there, so 1 times 10 to the minus 10, whereas the Hubble is 171 times 10 to the minus 9. So if I then compare them, this is the angle that I need to be able to resolve. 76 times 10 to the minus 9 is smaller than 171 times 10 to the minus 9. Therefore, the Hubble is unsuitable. Okay, it can only resolve things that are bigger than 171 times 10 to the minus 9 radians. However, 76.5 times 10 to the minus 9 is bigger than 1 times 10 to the minus 10 radians, so the EHT is suitable as the angular size is bigger than the resolution. And you can see here what you're getting your marks for. One is for doing one of these Rayleigh criterions, one is for using the Schwarzschild radius equation, using it, not just writing it down, you have to put the numbers in. One is for getting that this angle is 76 times 10 to the minus 9 radians, and one is for then doing both the Rayleigh criterions correct and writing a suitably correct conclusion. So then part C, a star is orbiting the black hole in M87. The star is observed in the plane of its orbit. The wavelength of a spectral line observed in the light emitted from the star varies between a maximum and a minimum value. Calculate the orbital speed of the star. So I'm going to be using the redshift equations here. Z equals minus V over C, and that equals minus delta F over F, or delta lambda over lambda. In the formula sheet, this is a plus and this is a minus, but it says V over C. So I'm just taking all my minus signs into account. The minuses don't really matter. So V over C, I'm going to choose equals delta lambda over lambda for reasons that will become apparent. I know C, I want to know V, I need to work out delta lambda and lambda. Now, the change in lambda is the change from the average. So the first thing I'm going to do is just work out the difference between these two, which is 1.43 nanometers, and then divide that by 2. Sorry about all these emails, it's the loud time of day. I'm just going to pause for a moment and mute them. and she's back. Or what I could do is a different way. I do need to work out lambda, and lambda is going to be the standard wavelength, which is going to be the average of these two, because it either gets red shifted or blue shifted. So when it's not being either, it's going to be in the middle. So I'm going to add them up and divide by 2. So this is your normal laboratory reference wavelength. So I can either, to work out the change in lambda, do the difference between the two divided by 2, or I could do this minus this, or this minus this, and work out the change, and it should be the same. What I should find is that delta lambda is 0.715 nanometers, and the average lambda is 374.245 nanometers, and I just put those into the equation. So the change in divided by the average times by the speed of light, and you get 573 times 10 to the 3 meters per second, which is 5.7 times 10 to the 5 meters per second. Okay, 2 questions to go, and the next one is a big one. So, M40A and M40B are 2 stars that appear very close to each other when viewed from Earth. There are 2 possible reasons for this. 1, they're in an orbiting binary system, or 2, they're distant but they just appear to be in the same line of sight. In an orbiting binary system, the difference between the apparent magnitude and the absolute magnitude for each star is similar. The table below shows data about these stars. Discuss the appearance of the 2 stars to an astronomer on Earth. In your answer, you should compare the colour, compare the brightness, and deduce with a calculation whether the stars form an orbiting binary system. So we're going to do this step by step. For 6 marks, you have to cover all 3 areas and do them in detail, but you are actually allowed to make a mistake and still get 6 marks because it's quite a lot to do. So first things first, we are going to compare the colour of the stars, and we do that using, you guessed it, once again, let me just get it back up again, this table. So using this table, we can see that M40 is a class F/G star, and M40B, is class K. Now this is the order, remember, O be a fine guy or gal, kiss me, from hot to cold. So A is on the border of these 2 and K is there. We can also see from that table what their colour is, and we can see that we've got yellow, white, white, or orange as our options there. So I'm going to write that down to start with. Okay, so for my first thing, M40A is an FG class star, and so will be white or yellow white. M40B is a cooler K class star, and so will be redder because it's cooler and it is in fact orange. Next is compare the brightness of the stars. Now, apparently, or their apparent brightness, M40A has a lower apparent magnitude and therefore will be brighter. Not much brighter though, and we can figure out how much brighter. So M40B is dimmer because it has a higher apparent magnitude. The difference is 0.4. Now remember, every 1 step, so from like 9 to 10, is 2.51 times brighter. So A is going to be 2.51 to the x, which is 2.51 to the 0.4, which equals 1.5 times brighter on Earth than B. But we now need to do the hard part, which is thinking about, deduce with a calculation whether the stars form an orbiting binary system. Now, we're told in an orbiting binary system, the difference between the apparent magnitude and the absolute magnitude for each star is similar. So we need to calculate something to do with absolute magnitude, which links to the actual brightness of the star. We don't actually have to find out absolute magnitude, but we have to find out something absolute, and we're going to find out the power of the star because we've been told the temperature and the radius. So we can work out the power output of the stars using Stefan's law. P equals sigma surface area times t to the 4, and surface area is 4 pi r squared. So I'm going to work that out for both A and B. So 4 pi sigma are both the same, but then I've got r squared, so for A and for B, and then the temperature to the 4. And we see that A has a power or a luminosity of 3.66 times 10 to the 28, whereas B has a luminosity or power of 4.22 times 10 to the 28. So B is actually brighter or more powerful than A because it has a higher luminosity, even though it's dimmer. Now, if I need to have, if I go up here, the difference between apparent and absolute magnitude for each star would be similar, well, B should therefore, if they were in a binary system, if this is how they apparently look, their absolute magnitude should follow the same pattern. So A should actually be brighter than B. But as B is actually brighter than A, that means there's going to be a larger difference in this difference between n minus m. So that suggests that they're not a binary and they're just in the same line of sight. And then finally, question 5, we've got some cosmology going on here. We've got Hubble's graph, and it says estimate using the graph above the age of the second and age in seconds of the universe. Now, whenever you see this graph, you should be thinking gradient is Hubble's constant, age is approximately 1 over that. So I've gone for that route. You have to draw a line of best fit, and it should go through the origin because a galaxy that's not moving away from us is not far from us. So it should go through 0, 0. You will not get your line of best fit mark if it doesn't. And then you're going to work out your gradient, which will be a different number to mine. But remember, they want it in seconds, and this gradient's in kilometres per second and megaparsec. So you have to take into account the fact we've got kilometres. So I got here, you can see that y is 12,000 times 1,000 for kilometres, and then 180 megaparsec, so it's mega, and then this is a parsec, and that gives me a gradient of 2 times 10 to the minus 18 s to the minus 1, which I know is about right. Now, I know that age is 1 over gradient, so I'm going to do 1 over that, and I get 4.6 times 10 to the 17 seconds, which is bang in the middle of the accepted range, and you could check turning that into years. It should be around 14, 15 billion years. You could, of course, instead of doing what's the gradient, what's 1 over, you could just do x over y instead of y over x, and that would still give you the same answer. What they won't allow you to do is say, oh, the formula sheet says the gradient should be 65 kilometres per second per megaparsec. You have to actually find the gradient out for yourself. And then final question, nice and easy. The estimate in part A assumes that the universe has expanded at a constant rate. Measurements involving type 1a supernova that are at large distances from Earth caused astronomers to make a modification quite recently in the past 10-15 years to this assumption. What is the modification and what's the explanation? Well, we find out that actually the universe is expanding at an accelerating rate, and we think that's because of something called dark energy, which is the expansion force, I'd say counteracting the pulling in force, which is gravity, which is due to the mass of the universe. So you couldn't write dark matter because dark matter increases the gravity of the universe, which would not accelerate the expansion. You have to write dark energy. Hopefully that was useful. That was just a quick run through. Worth reading the examiner's report if you can as well, and hopefully it helped.